Let me now describe the 3 thought process limitations that play a determining role in my Benny decision. I will use a problem-solving exercise to describe each. The first problem is called the mutilated checkerboard problem. You are given a checkerboard with 64 squares, and you are given 32 dominoes. Can you arrange the 32 dominoes so they cover the 64 squares? Of course you can. There are thousands of different patterns of the 32 dominoes that can cover the 64 squares. Now remove 2 squares from the checkerboard and 1 domino from the stack of 32 dominoes. Is there an arrangement of the 31 dominoes that will cover the 62 squares? When you offer this problem at a cocktail party, you will give time to your guests to show how clever they are. However, since our objective is to understand limitations in our cognitive process, let me plunge forward. Realize that covering 62 squares with 31 dominoes is a much harder problem. Instead of having thousands of patterns that will work, this problem has thousands of patterns that won't. I could come back tomorrow, and while you might have tried hundreds of non-working patterns, you would still not know if there was one or more pattern that would. So let me give you another problem that will help you see a simple way to tell if 31 dominoes can cover the 64 squares. It's called the Matchmaker Problem. In a small Russian village, there are 64 unmarried people. 32 women, 32 men, and because of extreme skill, the matchmaker has arranged 32 engagements. To celebrate this feat, they throw a party. At the party, there is a fight, and 2 of the bachelors are killed, leaving 32 women and 30 men. Can the matchmaker make 31 engagements out of the remaining 62 people? Of course not. While there is an even number of individuals, 62, the matchmaker, after creating 30 matches, will find she is left with 2 women. Not a match, at least in terms of her original objective. Now back to the mutilated checkerboard problem. Notice that a domino connects 1 black and 1 white square, like a marriage connects 1 man and 1 woman. Also notice that the 2 removed squares are both white, like the bachelors who died. After 30 dominoes are used to cover 60 squares, 30 black and 30 white, the 2 squares that remain uncovered will both be black, like the 2 unmatched women. Notice there is no place on the checkerboard where 2 black squares are side by side, like states that ban gay marriage. Therefore, there is no way the 31st domino can cover them both. Therefore, 31 dominoes cannot cover the 62 squares. The tool used to make solving the problem easy I call coupling. And coupling creates groups. And dealing with the groups instead of many single units leaves a smaller number of relationships to visualize. This greatly reduces mental computation and makes the problem easy to solve. Now let's investigate a second limitation in my thought processes. I will use the monk problem to demonstrate it. In the monk problem, there is a mountain. At the bottom of the mountain is a monastery. At the top of the mountain is a small shrine. There is a path connecting the 2. A monk rises early and gets on the path at exactly 7 a.m. And as he walks, he stops several times to eat, rest, and watch birds. He arrives at the shrine at the top of the mountain at exactly 7 p.m. Next day, he rises, gets on the path down at 7 a.m., while stopping and resting wherever he wants. At the end of the day, he arrives at the monastery at exactly 7 p.m. Does there have to be a spot on the path where the monk was present at the same time on the way up as on the way down? This is another wonderful problem for a cocktail party. Challenge your friends to declare, yes, there has to be such a spot. No, there does not have to be such a spot. They could spend the better part of the evening arguing. Here we will stay focused on describing a second limitation in my thought processes and a way of overcoming it. Let's reduce the computational complexity by using two monks on the same day. One monk starts up from the bottom at 7 a.m. with walking directions that match the original monk's trip on the first day, and a second monk down from the top at 7 a.m. with walking directions that match the original monk's descent on the second day. Do the two monks have to meet somewhere on the path? Yes, and where the two surrogates meet is the point on the path and the time of day when the original monk was at the same place at the same time on his trip up as on his trip down. Getting two processes that happen on different days to happen on the same day is called simultaneity. Simultaneity reduces mental computation and makes the monk problem easier to solve. Let me provide a second way of creating simultaneity. Draw two graphs for the monk's two trips. Each shows the time that the monk was at each elevation. One graph for the climbing day and one graph for the descending day. Then move one graph on top of the other. And that point on the path and that time of day when the rising monk and the descending monk were at the same point at the same time. You have seen two tools that overcome these limitations, coupling and simultaneity. Each makes a complex problem a little easier to understand and solve. Now, wasn't that fun? I hope you will join me for one more illuminating puzzle.